In this chapter, we will talk about trigonometry of right angle triangles. Let's first draw a right angle triangle and call it ABC. The sides AB and BC are perpendicular to each other, and this angle at B is said to be 90 degrees or called as a right angle. The longest side of a right angle triangle is called hypotenuse. There is a very famous theorem called Pythagorean theorem, and it states that the sum of the squares of the lengths of the sides of a right angle is equal to the square of the length of the hypotenuse. Okay, so let's put that into writing. So sum of the squares of the lengths of the sides. So sum of the squares. So of the lengths. So AB. What are the sides here? The sides are AB and BC. So the sum of the squares, lengths of the squares, right? So AB square plus BC square is equal to the square of the length of the hypotenuse. So this is equal to AC square. For instance, if AB is A units in length, BC is B units in length, and the hypotenuse is C units in length, Pythagorean theorem states that A square plus B square equal to C square. So given this formula, and if you are given two sides of the right angle triangle, you can find the third side pretty easily, and we will see some examples in the next lesson. So now let's draw a right angle triangle, and name it A, B, C. If AB is 3 units in length and BC is 4 units in length, what is the hypotenuse length? So Pythagorean theorem states that sum of the lengths of the sum of the squares of the lengths of the sides is equal to the square of the length of the hypotenuse. In this case is x square. So let's assume this as x. So as you see, x square is 9 plus 16, which is equal to 25. So taking square root on both the sides will make it x equal to root of 25, which is equal to 5. So in this case, the hypotenuse x is 5 units in length. Let's see one more example. So if I gave you a right angle triangle, and one of its sides is 6 and the hypotenuse is 10, what is the other side? So again, applying the Pythagorean theorem, sum of the squares of the lengths of the sides. So a square plus 6 square is equal to the square of the length of the hypotenuse, which is 10 square. So a square plus 36 is equal to 100. So a equal to 100 minus 36, which is, a square equal to 36, which is 64. So taking square root on both sides, a is equal to 8 units in length. So the side of this triangle is equal to 8. So this is how you apply the Pythagorean theorem. We'll look at another example where we will use the Pythagorean theorem. So consider an isosceles triangle. An isosceles triangle is a triangle in which two sides are equal. So for instance, this is side 8, this is side 8, and this is 6. So if you were asked to calculate the height of the isosceles triangle, So the way we do it is, the height of the isosceles triangle is determined by the line segment that is perpendicular to the base of the triangle and extends all the way to the vertex of the opposite angle. So we draw a perpendicular line from the base, which is BC, and extend it all the way to the vertex of the opposite angle, which is A. And this line segment divides the base into exactly two equal segments. So if you call this as D, BD would be 3 and DC would be 3. Now as you see, we have formed a right angle triangle ADC. So triangle ADC is a right angle triangle. So the problem asks us to calculate the height h of this isosceles triangle, and we can do that by simply applying the Pythagorean theorem to the right angle triangle ADC. So let's apply the formula. So the Pythagorean theorem says that the sum of the squares of the lengths of the sides. So what are the sides of this right angle triangle ADC? So the sides are AD and DC. So AD square plus DC square is equal to the square of the hypotenuse, which is AC square. So now let's substitute the values. AD is h, so h square plus DC we have calculated that to be 3, so 3 square is equal to AC, which is the hypotenuse, in this case is AC, which is 8 square. So that means h square plus 9 equal to 64. Square is equal to 64 minus 9, which is h square equal to 55, which is h is equal to root 55. So the height of the isosceles triangle, height of the isosceles triangle ABC is equal to root 55 units. So this is how you can calculate the height of the isosceles triangle by applying the Pythagorean theorem. Let's look at one other example of the Pythagorean theorem. Consider this right angle triangle. ABC D. So as you see, the triangle ABC is a right angle triangle with the right angle at A. Similarly, there is a line segment AD which has created two other right angle triangles ADB and ADC. So let's look at this. The triangle ABC is the big triangle, which is a right angle triangle. Similarly, the perpendicular line segment AD to the base BC has divided it into two smaller right angle triangles, which are triangle ABD and triangle ADC. So if we are given this height of this Pythagorean theorem, height of the right angle triangle to be 2 root 5, and the base is divided into two different line segments 3 and 4, and you are asked to calculate A and B, it's quite simple to do by applying the Pythagorean theorem to the two triangles ABD and ADC. So let's look at it. So for the right angle triangle, which is on the left side ABD, AB is the hypotenuse, which is A, and the sides are 3 and 2 root 5. So Pythagorean theorem states that A square equal to 3 square plus 2 root 5 whole square. Okay, so let's calculate that. 3 square 9 and 4 times 4 square into 5. So a square is this is 2 square, and that is root 5 whole square is 5. So 9 plus 20. So a square is 29. So is a equal to root 29. Similarly, applying the Pythagorean theorem to the angle which is on the right side. Here the hypotenuse is AC, which is B, and the sides are AD and DC, which are 2 root 5 and 4 respectively. So Pythagorean theorem says that B square equal to 2 root 5 whole square plus 4 square. So that is nothing but B square equal to, again, 2 square is 4 and root 5 whole square is 5 plus 4 square is 16. So B square is 20 plus 16, which is equal to 36. So B equal to root 36, which is equal to 6. So in this triangle ABC, AB, which is A, turned out to be root 29, and AC, which is B, is turned out to be 6 units. So let's look at the trigonometric ratios. Consider this right angle triangle ABC with the right angle at B. Let's call this angle C as theta and A as beta. So the first trigonometric ratio that we will learn is called sine of an angle, and which is in short called sine. So the sine of the angle is equal to the length of the opposite side by the length of the hypotenuse. So in this case, sine of theta is equal to the length of the opposite side. So this is the opposite side, and the length is A. Actually, let's write it down in little detail. So let's call it opposite side divided by hypotenuse, which is equal to AB by the hypotenuse AC, which is equal to A by C. So the sine of an angle is opposite by hypotenuse. In this case happens to be A by C. So this AC is the hypotenuse. The next trigonometric ratio that we will learn about is called cosine, or in short cos. And here the cos of an angle is defined as the adjacent side divided by its hypotenuse. So cos theta in our case would be like adjacent by hypotenuse is equal to the adjacent side, which is adjacent side is BC divided by the hypotenuse, which is AC, which is equal to B by C. The third one is tangent of an angle, or in short called as tan. So in this case we are going to calculate the tan of theta. The tangent of an angle is defined as opposite side divided by the adjacent side, which is in this case opposite side is AB, the adjacent side is BC, which is nothing but A by B. So the next three ratios that we talk about are reciprocals of the first three ratios. So we will begin with cotangent, which is also in short called cot theta, is defined as adjacent by opposite. So as you notice, cotangent is a reciprocal of the tangent theta. Cot theta is equal to 1 by tan theta. So this will be BC by AB, which is nothing but B by A. Similarly, the next ratio that we will talk about is called secant theta, which is reciprocal of cos theta. So that makes it hypotenuse by adjacent, which is equal to, in the R case, AC by BC, which is C by D. The last ratio we talk about is, this is called secant. The last one is called cosecant, or in short called CSC of theta, is actually a reciprocal of sine theta, which is hypotenuse by opposite, which is AC divided by AB, which is C by A. So these are the 6 different trigonometric ratios that we will be using in our course. So let's recap. So sine theta is defined as opposite by hypotenuse. Cosine or cos theta is defined as adjacent by hypotenuse. Tangent or tan theta is defined as opposite by adjacent. Cotangent, which is the reciprocal of tan theta, is defined as adjacent by opposite. Secant, which is the reciprocal of cos theta, is defined as hypotenuse by adjacent. And cosecant, which is defined as reciprocal of sine, is equal to hypotenuse by opposite. So going back to the previous lesson, we have defined 6 trigonometric ratios, and the first 3 are sine, cosine, and sine, cosine, and tan. And the last 3 are essentially the reciprocals of the first 3. So the reciprocals here are cot for tan, secant for cosine, and cosecant for sine. So is there an easy way to remember these formulas? So there is a secret mantra which is called Sokata, Sokatwa. So let me write that. So ka toa. So if you say this mantra, which is Sokatwa, you can easily remember this. So what do I mean? So let's look at this. So, which is sine of an angle is equal to opposite by hypotenuse. The cos of an angle is equal to adjacent by hypotenuse. The tan of the angle is equal to opposite by adjacent. So say it one more time with me. Sokatowa. So if you say Sokatowa, then you can essentially remember all the 6. Wait a minute. So these 3 are just telling us about the 3 trigonometric ratios, and how can I remember 6, right? So as you know, the first 3 are primary ratios, and the next 3 are essentially the reciprocals of the first 3. So if you can remember the first 3, it is easy to derive the other 3 formulas by just changing the numerator and denominator of the ratios. So Soka Towa is your friend in trigonometry. So always remember this mantra and you will be very successful in trigonometry. So let's practice this mantra. So previously we have calculated the sine, cosine, tan, cot, secant and cosecant for theta, and let's now calculate the same for the angle beta using the mantra Soka Tova, right? So let's apply the mantra Soka Tova for sine, right? So sine beta is equal to, so opposite by hypotenuse. What's the opposite of beta? That's the opposite, and that is b by hypotenuse is c. And cosecant is the reciprocal of sine. So cosecant beta is C by B. Now, going back to the mantra, the second one is ka, which is adjacent by hypotenuse. So in here, cos beta, what's the adjacent side of beta? A, and hypotenuse is C. So secant beta is reciprocal of cos, which is C by A. Lastly, the third syllable of the mantra is toa. So tan B is toa. Toa. O for opposite, A for adjacent. So what's the opposite side? B. And what's the adjacent? A. Cot is a reciprocal of tan, so that is A by B. So this mantra makes trigonometric ratios very simple to remember. So ka towa. Okay, so let's look at an actual example. So this is a right angle triangle A, B, C. And sides are 3, 4, and 5. Calculate the 6 trigonometric ratios for the angle theta. So our mantra is ka toa, right? So sin theta is equal to opposite by hypotenuse. So 3 by 5. Cos theta, which is ka, adjacent by hypotenuse. And tan theta is toa, opposite by adjacent. So these are the three primary ratios. And now let's calculate the reciprocal ratios. Cot theta is 1 by tan theta, which makes it 4 by 3. Secant theta is 1 by cos theta, which makes it 5 by 4. And last, cosecant theta is 1 by sin theta, which makes it 5 by 3. Let us work through few more examples. Consider this isosceles right angle triangle. The sides of this isosceles right angle triangle are 3 and 3 respectively. This is theta. The problem here asks you to calculate cosecant theta. So how do you do that? So we'll write our formula. Ka toa. We know that from the mantra, sin theta is equal to opposite by hypotenuse, and cosecant theta is nothing but a reciprocal of sin theta, which makes it hypotenuse by opposite. So if you look at this example, we do not know the length of the hypotenuse, but from Pythagoras theorem we know that sum of the squares of the lengths of the sides is equal to the square of the length of the hypotenuse. So 3 square plus 3 square is equal to h square. So that is h square is equal to 9 plus 9, which is 18. So that makes h square equal to h equal to root of 18, which is 9 times 2 is 3 root 2. So now that we know h is equal to 3 root 2, calculating cosecant becomes very easy. So cosecant theta is hypotenuse, which is 3 root 2 divided by the opposite side of theta, which is AC, and that is 3. So cosecant theta turns out to be root 2. In this lesson, we will derive the relationship between sine, cosine, and tangent. So let's draw a right angle triangle ABC with the right angle at B. Let's consider this as the T. So our mantra again is Soka Toa. It says that sine theta is equal to opposite by hypotenuse and cos theta is equal to adjacent by hypotenuse and tan theta is equal to opposite by adjacent. If you observe closely, if you divide sine theta by cos theta, so sine theta divided by cos theta is opposite by hypotenuse divided by adjacent by hypotenuse, which makes it opposite by hypotenuse times, take it out and say hypotenuse by adjacent. Hypotenuse cancels out, so you'll end up with opposite side by adjacent, which is nothing but, if you look here, opposite by adjacent is tan theta. So in any right angle triangle, tan theta is equal to sine theta by cos theta.